G'day mate, today you're going to be taking yourself through some proofs. Right, so the first one's quite simple. The absolute value of z, or the distance from the origin, is greater than or equal to 0. Equality holds if and only if z equals 0. Alright, now let's just highlight the second one, because this is the one that we're going to need to do all the other proofs. Yeah? It is that the conjugate of z times z is x squared plus y squared, which you should already know from realizing the denominator. And the conjugate of z squared is x squared plus y squared. Yeah? Now, with this, you can try to start with the values, find their respective distances, but the faster way to do it is to square it. That's not big enough. Give me a second. Boom, bigger. Conjugate of z squared. Now, you should know that that'll be equal to conjugate of z, the conjugate of z times the conjugate of the conjugate of z, y, b. Now, the conjugate of z is very obviously just the conjugate of z, which gives you just that. Where have you seen that before? Also b. Therefore, that is equal to z squared. Now, if the conjugate of z squared equals z squared, obviously the conjugate of z is equal to z. Boom, I'm down here now. So, for this one, it's pretty much the same. You square that and use b, which will tell you that that is the case. Alright, now, negative z times the conjugate of negative z, yeah, is just negative 1 squared, so 1, times z times the conjugate of z. What's that? There, same situation. Boom, back here now. Alright, let's go ahead and square the absolute value of zw to prove that the product of the absolute values is equal to the absolute value of the product. Fancy. Alright, so you would get that times the conjugate of zw, y, again, that, you're just inputting this here and this there. Alright, that, if you just rearrange it, it's going to give you this. You're not doing anything algebraically, you're again just rearranging it. From that, you can say this is the case. Z squared times w squared. Done. Boom. Down here again for the explanation of the fourth one. That is that the quotient of the absolute values is equal to the absolute values of the quotient. So just the one from before in reverse. You can take both of these and multiply them by the absolute value of w. However, you've proven in this one that if you multiply something by the absolute value of w, it's the exact same thing, it's just adding the multiple of w into the absolute value. So, you get that. And this just becomes the same with a little times absolute value of w there. Okay? Therefore, this cancels out. So you've just got the conjugate of z up here. Now, the conjugate of z is equal to that times w. You just want to spin that around, and you got that there. Didn't quite understand this one, but hey, the teacher gave it to us. And I'm not going to argue with this, am I? No. Alright, now to prove that the real of z and the imaginary of z are greater than or equal to z, you do the same sort of thing, so I'm just going to save time and just do 1. Alright, let's get into my little squatting proving position to say z squared is equal to x squared plus y squared. Where did I take that? Duh, the same place I've been taking everything all night. Alright, therefore, obviously, yeah, z squared must be greater than or equal to just x squared by itself. Now, to get rid of these, you can't just rub them out. You have to separate them. You have to say that x is less than or equal to the absolute value of x. Why? Because if x is negative, yeah, and only if x is negative, then that's going to be way less. Yeah? If it's positive, it's going to be equal to the absolute value. And then that is going to be less than or equal to z. Now you know that x, if z equals x plus iy, is equal to the real part of z. Therefore, if you just take this, ignore that, you have just proved that x is less than or equal to z. Same thing goes for y. Okay, now the last one we're going to prove today is the conjugate of z plus w is equal to the conjugate, no, not the conjugate, the absolute value of z plus w is equal to the absolute value of z plus the absolute value of w. Now, how we do that is, like the others, we will square it. Okay? Which you know to be this. Yeah? From B. Now, if you just expand that, you'll be able to prove that it is equal to conjugate of z plus the conjugate of w. Yeah? Expanding the brackets, you're going to get z times conjugate of z plus z times conjugate of w plus w times the conjugate of z plus w times the conjugate of w. Alright, now these two on the far side, they're applicable to B. You're going to have that and that. So the absolute value of z squared and the absolute value of w squared on the other side. Now, these two added up, yeah, can be separated and reattached to give you 2 times the real of z conjugate w. Okay? You just again expand it. Now, this also gives you the inequality. Sorry. Less than or equal to z squared plus 2 times the absolute value of z conjugate w plus that. Alright. Why? Because you have proved in the last one that the absolute value of a complex number is less than the real aspect of the complex number. Therefore, all that is going to be less than all that. Therefore, that is going to be less than that. You've also proven in one of these that you can separate the two. Okay? Which is going to give you, so they're equal to conjugate of z squared. Sorry, the absolute value of z squared plus 2 times z w plus w squared. Anyone in MATH132 should be able to tell that that is just going to look like that. Yeah, straight away. You've been factorizing square things for centuries now. Right? Therefore, that squared is less than that squared. Okay? Therefore, z plus w is less than or equal to conjugate the absolute value of z plus the absolute value of w. This was wrong. This should have been that. Trouble with my notes. I apologize. Now, yeah, that was fucking hard. I hate proofs. This video took me 25 minutes to do. Appreciate it.